ferromagnetism at a higher level of sophistication. Previously, we've seen Weiss's molecular field theory, which is a mean field theory in the sense that each spin within a domain sees the same molecular field, B and F. So there is a mean magnetic field that is seen by each and every spin inside the domain. And this mean field is lambda m plus some external field if it is applied. For a ferromagnet, m is the magnetization of the domain itself. And for an antiferromagnet, m is the magnetization of another sublattice. So this is a mean field theory. And we've seen that for the mean field theory, we have results, predicted results for the magnetization m over ms versus the temperature, the reduced temperature for a ferromagnet. However, when experiments are the final arbiter for any model, the experiments will decide whether the model is correct or not, and how accurate is the model, how strong or how formidable is the predictive power of the model. So this is a very good model, but it breaks down under certain circumstances, especially at low temperatures. And if you look at the data points at low temperatures, the magnetization is actually smaller than what is predicted by the mean field theory. And this theory has some other handicaps as well. Now, in order to overcome these handicaps, a more refined version is, a more refined model is necessary, and that is the model of spin waves. And this model can describe ferromagnets, antiferromagnets. Now, in order to introduce spin waves and magnons, what we need to understand is the following. Suppose I have a one-dimensional ferromagnetic chain. Of course, this is the lowest energy configuration if J is positive. And the energy that is associated with this ferromagnetic chain, if there are capital N spins, each spin is S, then how many pairs do we have? We have N minus 1 pairs. So the exchange energy associated with this one-dimensional chain is minus 2J. Suppose that there are only nearest neighbor couplings, and the coupling strength is J. So this is minus 2J S dotted with S, which is S squared. And how many pairs do we have? We have N minus 1 pairs. So this is the exchange energy associated with this one-dimensional ferromagnetic chain. Alright? N, we suppose, is a large number. Now suppose I have this large ferromagnetic one-dimensional chain, and I would like to make an excitation. That is, I would like to increase the energy by 1 unit, whatever that energy is, whatever that amount of energy is. So what I would do, I would flip just one spin. This is what I would naively do. So this is the first excited state for this one-dimensional chain, as far as the exchange interaction is concerned. So it's an excitation. It's a spin excitation. Alright. Now if you would like to compute the energy of this state, first of all, we're doing a thought experiment. Second, yes, we can apply a field that only addresses one spin, which is localized, such that it addresses one spin. This is not always easy to do. You can do this actually with light sources. If you have, say, a trap of ions, it won the Nobel Prize of Physics a couple of years ago. You have a trap of ions which are separated by some distance, and there is a finely tuned laser beam that just addresses one of the ions, you can achieve selective 180 degree rotation of spins. Yes, you can do that. But it's not trivial. So if you would like to compute the exchange interaction energy associated with this configuration, there are n minus 3 pairs, so 2 less pairs in which the interaction is of this kind. And there are 2 pairs, one is this pair and the other is this pair, in which the interaction has become positive, because neighboring spins are now anti-parallel. So this becomes 2j s squared and 2 times this, because there are 2 pairs, one is this pair and the other is this pair. Remember, we're only considering nearest neighbor interactions. Other interactions fall off. The interaction of one spin with the second nearest neighbor is 0. So this is the new energy. So it is minus 2j s squared n minus 1 minus 2j minus 2 plus 4j s squared, and this is 8j. This thing minus 2j s squared n minus 1 plus 8j s squared. So the energy of this configuration in exchange, the exchange energy has gone up by 8j s squared units. Now this s could be a spin half, could be 1, it could be 3, but it could be anything. So now just flipping one spin, that is creating an excitation, increases the energy. In the mean field theory, the Weiss's molecular field theory, we assume that all the spins see the same field, and all of these spins are in the ground state. However, temperature will have some effect, number one. The first effect is that of temperature. The temperature will misalign these spins. It will not, if you increase the temperature above 0 Kelvin, the magnetization need not be at the saturation level. So there could be excitations in the spin system. Okay? So one is that we have to take into account the effect of temperature. How do we do that? We can of course define a new lambda which is temperature dependent, which makes the molecular field temperature dependent. We can incorporate the temperature dependence into lambda, but we can also do cleverer things. Now another limitation of the molecular field theory is the following. So I will introduce the concept of an excitation. One spin is flipped, that can be treated as an excitation of this chain of spins. Excitation is anything that has a higher energy. For example, if you look at the harmonic oscillator and you look at the energy levels, so if this corresponds to light trapped inside a cavity, the energy could be this much, but you can add more photons to the system. A photon can be created. So you can increase the number of photons inside the system and go up the ladder in this harmonic oscillator, in this energy scheme. So these states correspond to excitations, and an excitation is actually the creation of a photon. More photons are going into the system. Correct? Likewise, we can talk about phonons. Lattice oscillation, excitation is lattice vibrations. These are called phonons. Now what we're trying to do is, we're trying to look at spins. Now suppose we have this configuration, the perfect ferromagnetic configuration. The magnetization of this system is at its maximum value, ms. Now suppose what I would like to do is, I keep the number of spins the same. Let me draw some more spins so that I can draw a better diagram. Now what I would like to do any two neighboring spins, they are slightly displaced by a certain angle. The magnetizations are tipped by a small angle. So they're not all in the z direction. They make a certain tip in the xy plane. So one way of drawing this system is the following. This spin is up, slightly tilted. Okay. So now what we have is we have the same number of spins. The spins are separated by some real parameter A, which is a lattice constant in the magnetic unit cell, and the spins are now slightly canted with respect to one another. They're slightly tilted with respect to one another. Okay. What's the magnetization of this chain? If the spins are going in making a complete circle, the magnetization of the system is 0. Because you add up all of these vectors, you get 0. Alright? So one spin is pointing up, the neighboring spin is slightly down, so all of the spins are canted. And if you go around this complete, if you go around n times a units, you make one complete cycle. Now the magnetization of the system is 0. However, so the molecular field theory would say that this system is a highly energetic state because the magnetization is 0. Right? So we know that the energy is given by minus m dotted with b. So this is the lowest energy state in which m is maximum. Now if m goes to 0, it's the highest energy state, which is pitched at energy 0. So it's a very high energy state. However, from an exchange perspective, if you look at two neighboring spins, the angle between these spins is really, really small. So the energy between any two spins in a pair, we all know, is given by minus 2j s1 dotted with s2. Now S1 dotted with S2 is a small, this is minus 2j s squared cosine of theta. Theta is really small. So this is almost minus 2j s squared up to the 0th order. Right? So this energy is still small. The energy of interaction between any two spins is still small. And the energy of interaction between any two neighboring spins remains small. So the energy of this system is actually quite small. But the mean field theory would have us believe that since the magnetization of this overall system is 0, the energy is really high. In other words, what we've done here, suppose we peg one, this is a string. This is a string. And we peg one end of the string, take the other string, and rotate that other end by 360 degrees. This is actually what we've done. We have taken this configuration of one spin being in the opposite direction, being antiferromagnetically coupled to its nearest neighbors, and we have spread this spin flip over the entire chain. We have delocalized this spin flip over the entire chain. This is something you could do quantum mechanically, right? Okay, so this configuration is once again a low energy state, in a sense. But the mean field theory would treat this as a high energy state. Alright. Now where do we go from here? This kind of configuration is called a spin wave. Why is this called a spin wave? In reality, what we could have is that these magnetizations lie on cones. Remember that now we're treating these spins as classical objects. These are magnetization vectors. And the spins are on the surface of this cone, and they change their phase. So around one complete path, the tip of the arrow goes around by 2 pi on this circle. Now if you look at this from the top, we can draw circles. And these arrows, the locus of these arrows is shifting on these circles, which are the opening circles, which are at the apex of this cone. And if you connect these points to an arm, you get a wave, a single wavelength of a wave. So this kind of excitation, in which one end of the chain is effectively rotated by 360 degrees, and all the spins are displaced, canted with respect to one another by small angles, right? By small angles is a spin wave of the next order, the first excited spin wave. We could also have a 360 degree rotation here, which means you will get two wavelengths in the same chain length. That will be the second excited spin wave. Alright? So that will be even of a higher energy. The energy of this system is going to be one unit, whatever it is, above the perfectly ferromagnetic state. So these are excitations in the spin system. The first excitation is just taking one spin and rotating it. So one spin is rotated, is made anti-parallel, but its effect is spread out over the entire volume of spins. This thing energetically will be the same as what I've written over there, this thing. The energy here is going to be the same, only that the spin delocalization is now spread out over the entire length of the chain. So these are called spin excitations or spin waves. Now what we would like to do is we would like to find out the dispersion relationship for these spin waves, and then we would like to introduce the concept of Magnons. Okay. Now what is an excitation? What is a photon? A photon is nothing but an excitation of the quantum field. What is a phonon? A phonon is the excitation of the lattice vibrations. Okay. So what we're doing here, we have the perfectly ordered state, which is zero energy, or minimum energy, sorry, the one at the top. And we are creating higher energy versions of this. The next higher energy version which we can create is an excitation, of course, is by having one spin flipped in the entire system. And the flip is delocalized over all the spins, so that any two neighboring spins are canted to a very small angle with respect to one another. Okay, so this is a spin wave of the first order. You can have higher orders. Changing the order means changing the wavelength. Higher order means shorter wavelength and higher frequency. Okay? Just as photons have frequencies, the spin waves also have frequencies. Alright. Now what we would like to do is, we would like to find out the dispersion relationship for the spin wave. And we'll do a classical derivation. If we have time, we'll do a quantum mechanical derivation as well. Let's find out the dispersion relationship for these excitations. Suppose I focus my attention on the nth spin, which is one spin out of this volume, nth spin. Now we've already seen that each spin sees an effective molecular field which is generated by the exchange interaction. Remember you by the molecular field theory. So the nth spin sees a molecular field BMF, which we all know is given by -2 over Gj mu b, right? Neighboring spins. J, the exchange interaction, and the neighboring spin's angular momentum. The neighboring spins are S, n minus 1. Now, since I'm doing a classical calculation, I'm putting a vector sign on top of this. Really, these are quantum mechanical operators. Plus, the next neighboring, one is to the left, one neighboring spin is to the left, the other is to the right. Sn plus 1. So this is really what the effective molecular field that spin sees is all about. It's the exchange interaction divided by this term into the angular momentum of the neighboring spins. Look at your notes from the previous lecture. Okay, this is the field that the nth spin sees, the effective field. Okay, Gj could be 2 for spin half particle, etc., etc. Now what's going to happen is that if you have the nth spin, it sees a field. So a torque will act on the nth spin. Okay? Now what we do know is that the torque that acts on a magnetic moment, mu, is mu cross with B. The torque that acts is the rate of change of the angular momentum. Right? S, and we also know that S equals Gj mu B mu equals Gj mu Bs. Mu equals Gj mu Bs. This is the gyromagnetic ratio. First or second lecture of our course. Which means that now we have this expression and we have this expression. So if you would like to find out the torque that acts on the nth spin, that's going to be given by mu cross with B. Now what's the magnetic moment of the nth spin? The magnetic moment is simply Gj mu B S of the nth spin crossed with the magnetic field that the nth spin sees, and that magnetic field is given over here. That's minus 2j over Gj mu B Sn minus 1 plus Sn plus 1. Some nice cancellations. I'm left with minus 2j Sn crossed with Sn minus 1 plus Sn plus 1. So spins exert a torque on neighboring spins. That's what it's all about. The strength of the torque is modulated by the exchange interaction. If you have two spins that are at a certain angle with respect to each other, they're going to be spin torque between the spins. And this is an important concept in spintronics. Now we would like to solve this equation and find out what Sn is. And from this equation we would like to find out the dispersion relationship. How does the energy depend upon K? And what is K? What is the meaning of K? We have to define that. Alright. Now what we would like to do is we would like to make certain simplifications. It's a nonlinear equation. It's going to be difficult to solve So what we assume is, suppose we have a spin in its ground state pointing in the z direction. Okay? And the spin is tilted. So the torque, so these spins are canted, okay? And how are they canted? They are canted to a certain, so this is S along the z direction, and this is slightly tilted through some angle, so that you add to this a new vector, say call it sigma, and you get Sz plus sigma. So this new vector is going to have three components. It's going to have a component along z, along x, and along y. But we would like this tilt to be really small. Okay? So this angle is really small because we want neighboring spins to be almost parallel to one another. So what we would like to do is, we would like to solve this equation under certain simplifications, that the canting between neighboring spins is small. And how does that feed into our equation? This is how it does. Suppose I would like to find out this cross product between two spins. Now if I take any two spins, Sn crossed with Sn, say -1. Let's find out this cross product. It's going to be Ex, Ey, Ez, Sn's x component, Sn's y component, Sn's z component, Sn minus 1's x, 1 y, Sn minus 1 z. Okay, this is what this is going to be. Now what I would like to do, I would like to define the following. I would like to say that my S and Z is almost S n, and I ignore terms that are of the second order, which means I would ignore terms like this: S alpha x, S alpha x, S beta x, S alpha x, S beta y, S alpha y, S beta x, S alpha x beta x, alpha x beta y, alpha y beta x, S alpha y, S beta y, where alpha beta is n or n minus 1 or n plus 1. Which means I would like to ignore terms that include products, mixed products, in which I'm taking the x component of one spin and the x component of the other spin, because this is really small. The x component is small. So likewise I ignore this term because this is second order in a small component. However, I will preserve terms. I will preserve terms of this kind. I will preserve terms such as S alpha z S beta x, S alpha z S beta y, S alpha z S beta z, etc. Okay, I will preserve these terms because S alpha z is almost the same as S. This is large and these are small. No doubt these are small, but these are first order terms, whereas these are second order terms. So I would like to ignore these second order terms. They're really small. So when I make these simplifications and I put the values in here, what do I get? I get differential equations. The first thing I would, which is immediately obvious, is I would get three equations for the three components of Sn. And what are those equations? So when you do the algebra, this is something for you to do on your own. If I can do it, so can you. One of these is that the Sn's z component with time is 0. Which means that to first order, the z component of each spin remains unchanged. Okay? Sn z to first order is unchanged. Let's call this S n. The other two equations are the following. Minus 1 over 2j dsn's x component derivative with respect to time is Sn's y component multiplied by Sn minus 1's z component plus Sn y component Sn plus 1's z component minus Sn minus 1 y component plus Sn plus 1 y component. Okay? I only have terms in which the x and y components are repeating only once at the most. The third equation is minus 1/2 dsn's y component is given by minus Sn's x component Sn minus 1's x component minus Sn's y component Sn minus x component n plus 1's x component plus Sn minus 1's x component plus Sn plus 1's x component. Alright, so these are the three equations. I would like to solve these equations. I know that the z component remains constant. However, solving these equations means that I need to find out what the x component of the n spins, angular momentum, and what the y component is. So I take ansatz, I take trial solutions. One trial solution is for the x component, say Snx. I take the traveling wave solution. Some a complex number E I. The traveling wave is defined by a wave number k. Since it's a discrete lattice, the spins only exist at discrete points on the lattice for the space variable at n times a minus some frequency. Now this is a wave, a traveling wave. Likewise, I can define the trial solution S and Y is some b E I k n a minus omega t. Now, what I would just like to do, I would like to put in these trial solutions into these equations, right? And I find out that these are indeed solutions provided I have the following condition. These are indeed solutions, and the constraints that come out are I omega b equals let me actually do this. Do you want me to do this way? Sorry. Reduce. Alright. You just insert this thing into this. This thing goes in here, and then you get two equations. One of these equations is I omega b is minus 4j sa 1 minus cosine of AA. And the other equation is I omega A equals 4JSB 1 minus cosine of AA. Alright. So what I've done, I've written down the torque equation for the nth spin. The nth spin sees a field. That field is created by exchange interaction with neighboring spins. Neighboring spins are slightly canted. Talking about the spin wave excitation, they're slightly canted. I take the assumption that terms that are second order in the deviations are small. Terms that are first order are preserved. To first order, we get these three equations. The z component remains fixed. It's the same for all of the spins. On top of that, only a small x and y component is added. And these are the trial solutions that work. So what we have is that the x component is like a traveling wave, the y component is like a traveling wave. The phase between these waves depends upon the relative angles between A and B, the complex numbers. This one? Inches, yes. Ye chota A. Oh, sorry. This is larger. Now we would like to solve these equations. These are just simultaneous equations, and what we get is quite simple. If you look at this equation, this is how you would solve this. I omega four Js 1 minus cosine Ka, and then here I have minus 4Js 1 minus cosine Ka I omega. This determinant has to be 0. I omega B is 4Js. Okay. Now this means I square omega square is minus omega squared minus this, which is plus 16 j square s squared 1 minus cosine Ka squared is 0, which means my omega squared is 4Js 1 minus cosine Ka whole squared. My omega is 4Js 1 minus cosine Ka. This is my dispersion relationship. It's also the same as 8Js sine square Ka over 2, right? This is the dispersion relationship. Now what is the dispersion relationship? It tells us the relationship between the energy, which is omega of the wave, h bar omega is the energy of the wave associated with this excitation. It relates this energy to k, the wave number or the wavelength of the wave. So corresponding to the spin excitation, the spin wave of some order, which is that order is defined by a wave number k or the wavelength k. This tells us which mode is being excited. Okay? Corresponding to that mode, there is going to be an energy. This is the energy. This is what the dispersion relationship is all about. So we can plot this dispersion relationship. We have omega here, we have k here. Remember, we talked about dispersion relation. We talked about the dispersion relationship of free electrons inside a metal. We can talk about dispersion relationship of quantized lattice oscillations, phonons. So this is the dispersion relationship of spin waves. Now we know that if I have Ka here, this is pi, this is minus pi. Okay, this function is periodic with respect to Ka with period 2 pi. So I'm just plotting the first Brillouin zone. So in the first Brillouin zone, if I plot this wave function It's a sine square curve, goes like this. This region is where Ka is approaching 0, which means this is a long wavelength region. If we are inside this region, we are exciting long wavelength spin waves. Long wavelength, small frequency spin waves. And the energy inside this region is small. Alright? This is the short wavelength region. High energy short wavelength region. For phonons, we all know, if you remember your solid state physics, for phonons, if we have Ka here, pi A, pi, we have minus pi here, what does the relationship look like? It's you remember? No, it's not the same. It's it is the same. Right? So it is the same. So for phonons, the dispersion relationship is omega square is K over M. 4 K over M under root sine square Ka over 2, right? So it's the same. So now we've derived the dispersion relationship for these spin waves. And the dispersion relationship is a relationship between A and the energy. Sorry, between K and the energy, the wave number and the energy. For phonons, it's not the same. For phonons, it's sine Ka over 2. Omega square for phonons, omega square is, this is 2. Omega square is 4 K over M sine square Ka over 2. So omega is so this is the dispersion relationship for phonons. Okay, it's not the same. It's a sine curve. It's like this. Sorry, I stand corrected. This is the relationship for phonons. This is the relationship for Magnons or spin waves. Notice in the small wavelength regime, the slope here is going to be different from the slope here. In the long wavelength regime, what we have is that Ka is small, this thing is small. When this thing is small, then our omega is almost 8Js. Now this is small, so I can replace this with K square, A square over 4. This becomes 2Js A square K square. So the omega is proportional to K square here. It's a parabola here. Whereas here, it's going to be a straight line. The relationship is linear. Remember, for phonons in the long wavelength regime, omega equals Vk. This is just an acoustic wave that is traveling in a lattice. So this is the dispersion relationship for a traveling wave, where V is the speed of sound inside that solid. Remember, we talked about phonons here. This curve applies to a monatomic lattice. Both of those, all of the atoms are of the same kind, and the coupling constant between these atoms is just uniform. Alright, so now we have the dispersion relationship for the spin waves. Now what do we do with this? Okay, we can do many interesting things. So the spin wave concept is naturally allied with the concept of a harmonic oscillator. Each new K that is produced corresponds to a new mode of the spin wave. And we can consider that associated with that mode there will be a certain number of particles. Each excitation can be treated like a particle. Such as, you have more light inside the cavity, there are more particles inside the cavity. Those particles are called phonons. Okay? You can have many phonons in the same mode. With the same K, you can have a large number of phonons, a large number of photons. So now these excitations correspond to these quasi-particles which are called magnons. And the energy of the spin system, if we have n magnons inside the system, is simply given by h bar omega, where we're talking about n magnons of frequency omega, n plus half. Alright, so this is the energy of a single magnon, h bar omega. Higher spin excitation means that means shorter values of K, shorter value of K, where shorter value of K, long wavelength, bigger value of K, smaller wavelength, corresponds to higher energies. Okay? So now the energy associated with each excitation is h bar omega. Alright, and this is the overall energy of the spin system. It's just like a harmonic oscillator. If the spin system goes, say, from K equals 1 unit to K equals 2 units, it's in a higher energy state. Correct? It's in a higher energy state, which means that more magnons, one additional magnon is being entered into the system. When an additional magnon is being entered into the system, it means one more spin is flipping inside the system. But its flip is delocalized over the entire volume. So one unit of angular momentum is being lost. If K goes to 3, another unit of angular momentum is being lost. So as more and more magnons are excited, the angular momentum of the system is going down. And associated with each angular momentum, we know that there is a magnetic moment, G mu B. So more and more magnons are being excited. The magnetization of the system is going down. Now how can more magnons be excited? They can be excited through temperature. Okay, so let's find out the dependence of the number of magnons on the temperature. Okay, the number of magnons tells us the level of excitation of the system, the energy of the system. So now what we would like to find out is the temperature dependence of the number of magnons that are excited. Of number of magnons. Okay. What we need to know first is that these magnons, like photons and phonons, these are bosons. These are spin 1 particles. Remember, adding one magnon to the system is reducing the angular momentum by 1 unit. So it's a spin 1 system, it's a boson. So each magnon is a boson. So the statistics that these bosons are going to follow are the Bose-Einstein statistics. which means that the number of magnons dependent upon the frequency at a certain temperature will be given by the Bose-Einstein distribution. So the number of magnons at a certain temperature per unit volume is going to be given by 1 over E h bar omega kBT minus 1. This is simply the Bose-Einstein distribution. Because these are bosons. Magnons are bosons, they are spin 1 particles. They have spin 1 because each one of them is contributing 1 unit of angular momentum. Each magnon that is being cited is equivalent to 1 spin flipping inside the system. But its flip is spread out over all the spins. Remember, it's delocalized. No. It's just one spin that is flipping anywhere inside the solid, but the effect is delocalized. This is one magnon is being created. You're moving up one ladder through the creation operator. You're creating a magnon. Okay. Now the number of magnons at a certain frequency and the temperature is given by the Bose-Einstein distribution. However, we also need to find out g omega, the density of states of the magnons, g omega. How many states are available for the magnons at a particular omega? Now we know for 3D systems that gk dk is, now gk is 4 pi k square over 2 pi cube over volume. So this is per unit volume now, dk. So this is 4 over 8, 2 pi square k square dk. So for a 3D system, we know that gk is given by k square over 2 pi square. What we need to find out is g omega for magnons, the density of states for the magnons. Now how do we find that? Alright. We know the relationship between the dispersion relationship. The dispersion relationship is omega equals 4js, or now let's look at the low temperature, the number of magnons at low temperature. Okay, so we're in this long wavelength regime. So omega equals 2js a square k square. This is my omega. So this defines the relationship between omega and k. So I'm using this expression over here in the long wavelength regime, which means I'm at really low temperatures. Right? I'm at really, really low temperatures. Okay. So this is my omega, which means I know what k square is as a function of omega. I need to know dk. Now, if I just solve this a little bit, it's just algebra, I get k square is omega over 2js a square, 2k dk is d omega 2js a square, which means my dk is d omega over 4js a square divided by k. Now what is my k? K is omega 2js a square 1/2. Okay, so I have dk and I have k. I just insert k square. I insert these values in here. My gk dk becomes k square. Now k square is this, omega over 2js a squared, small a squared. I have 1 over 2 pi square. I have dk. dk is d omega over 4js SA squared 2J SA squared over omega 1/2. So this gives me G omega. So let me work in this reverse order now. G omega is therefore given by, okay, now how do I solve this? This is, important point is that this is omega raised to power 1/2. Omega raised to power 1/2 this is 2JSA squared 2JSA squared 2JSA squared 2 मंथली 1/2 3/2 2JSA squared 2 मंथली 1/2 3/2 1/4 pi squared right. So this is my G omega. The important thing to notice is that it's proportional to omega 1/2. This is what you observe for electrons as well in the free electron model. Now what we would like to find out is the number of spins, number of magnons excited at certain omega, at a certain temperature, at a certain temperature. This is what we would like to find out. How many electrons are excited, magnons are excited at a certain temperature? Now what is this going to be equal to? This is going to be equal to 0, some upper cutoff frequency, omega c. That cutoff frequency is given, this is here. Because the total number of modes that exist in the system is cut off on the upper scale. So you have some upper cutoff frequency, which I'm going to change in a minute. Then you have V omega. Each mode has a frequency, so you integrate over all the frequencies. V omega. Then you would like to have the number of modes per unit volume, per unit frequency. That's G omega, which we've just calculated over here. And then you have the Bose-Einstein distribution, NV omega, function of temperature. This will give us the total number of magnons that are excited at low temperatures, at a certain temperature T, which is low. Right? So if I just put in these values, it's 0, d omega. Let's call, remember that now this term has a J in here. It has the exchange coupling constant in here, it has the spin here, so these are quantum mechanical quantities that are appearing inside this expression. So let me counter check with my calculation in the morning. 2J SA squared. And just, I have this extra pi square. Oh, A squared. I have this extra, maybe I was wrong in the morning, but anyway, this is some constant, right? Let's call this constant A. So this is A, omega 1/2, E, H bar omega, kBT minus 1. Now if omega goes up, this thing goes up, which means I'm at the upper limits of this integral. This factor, 1 over this factor goes really, really small. Correct? So when this factor goes, 1 over this factor goes really, really small, then I can take the upper limits to be infinity. Because this variable is being multiplied by a really small number for large values of omega. So I might as well go up to infinity so that I can solve this integral. So this becomes some A 0 to infinity d omega, omega 1 half e raised to h bar omega kbt minus 1. Alright. Now what I could do, I could take h bar omega kbt equal to x. This would mean omega is kbt over h bar omega, h bar into x. This would mean my d omega is kbt over h bar dx. Now I insert these values in here. I put this in here and I put this in here. So I get n as a function of temperature is A, d omega is kbt over h bar, but from omega raised to 1 half, I get another 1 half of this, so this becomes 3 by 2, 0 to infinity x okay. Now this is a standard integral. You can look up in a table, and its value is of the order of 1 to 2. It's small, it's just roughly equal to 1. So this is computable. Standard integral. The important thing that you observe is that the number of magnons that are excited at a certain temperature is proportional to the 1/5 power of the temperature. Alright. Now how does this affect the heat capacity? We know that now we know that at a certain temperature the number of magnons that are excited is 1/5 or the 3/2 power of the temperature. Okay, this is something we've seen. This does not come out from the molecular field theory. Now we would like to use some of these results to find out the magnetization, and we would like to find out the heat capacity associated with the magnons as well. So let's find out the heat capacity. You always do this kind of calculation for phonons in a basic solid state physics course. You do this for electrons. Now we're repeating the same kind of calculation for magnons, for excitations in the spin density. Okay? Now let's calculate the heat capacity. That's something simple to do. For the heat capacity, we need to know the total energy at a certain temperature. Now, the total energy, once again, is going to be given by an integral. It's some constant, which is the 0-point energy E naught, plus the energy of each magnon, which is h bar omega, g omega, which is the density of states of magnons, the Bose-Einstein distribution, and v omega, temperature, integrated over omega. This is the total energy of the system associated with the magnons. There is going to be some energy associated with the electrons, with the phonons, no doubt about it. But there is going to be a heat capacity associated with the magnons, and that will have a certain temperature dependence. So now if we put in all of this in here, we get E naught plus some A h bar 0 to infinity d omega. This is omega is power 3 by 2 e raised to power h bar omega kbt minus 1. This gives us omega raised to power 1 half. This gives us omega raised to power 3 by 2. Now if you make once again these substitutions over here. When we make these substitutions, we find out that the energy is given by T naught plus some constant omega रेज़ टू पावर 3/2 है, ओमेगा x 3/2 d ओमेगा, एक मिनट, ये 3/2 और ये 5/2, टेम्परेचर रेज़ टू पावर 5/2. Now we can calculate the heat capacity. And that will be, this is 0, this is the 0 point energy, it's immaterial. This is going to be 5/2 C, 5/2 C, T is equal to 3/2. So the heat capacity is turning out to be proportional to 3/2. Now if you look at electrons, free electrons, if you look at phonons, and if you look at magnons, the heat capacity for electrons varies as the temperature, at low temperature. For phonons, I think it varies as the third power of heat at low temperature. For magnons, it varies as 3/2. Magnons, by the way, inside ferromagnets. Magnons will also be excited inside antiferromagnets. This is something we'll probably do in the next class. And if we compute that, we will have a different dispersion relationship. A totally different dispersion relationship. And you will find out that the heat capacity will once again depend upon T is for 3. Remember, in the low temperature limit, omega is proportional to k square for electrons. It's proportional to k for phonons, and once again it's proportional to k square for magnons inside ferromagnets. So the last thing that you would like to do on your own is it's a simple argument about the magnetization. The magnetization is affected by the spin waves. If you had no spin waves, and if the magnetization was ms, in the presence of the excitation of magnons at a certain temperature, which is small, you are taking out angular momentum from the system. You're taking out angular momentum from the system. Each angular momentum unit that is being taken out carries with it a magnetic moment of g mu b. Now you're taking out n, which is a function of temperature, g mu b. This is the amount of magnetization that you're taking out from the system. Because each magnon carries a magnetic moment of g mu b, because it carries one unit of angular momentum. It's one spin that is being flipped associated with one quasi-particle, the magnon that is being excited. Now you have n of these at temperature. Now this n, we found out, depends upon T raised to 3/2. So now you have the dependence of the magnetization, which is of this kind, ms minus some constant v T raised to 3/2. So in the low temperature limit, the magnetization drops from the value that is predicted by the mean field theories. This law is also called the Bloch law. And this is a universal law. It's independent of the material. All materials will behave like this. Alright, now in the subsequent lectures next week, we're going to talk about different ferromagnetic phenomena in detail. We're going to talk about magnetostriction, we're talking about Landau theory of ferromagnetism, we're going to talk about ferrimagnetism, we talk about why is iron ferromagnetic, why is the magnetic moment for
why is it non-integer? So we're going to survey a large variety of different small topics in the subsequent